So that's the title, Turbulent Magnetized Gas in Molecular Clouds. It's work that I've done in the past year with Christoph Federeth and Mark Krumholtz, both at ANU. I spent a year in Australia as a sabbatical, and I'd highly recommend it to spend some time there. It's actually amazing. We actually took all those pictures. That's my little daughter. Okay. So giant molecular clouds. These are objects that contract out of the ISM. The ISM, as we know, is highly multi-phased, turbulent, supersonic, at least with respect to the cold components. And the density, a typical density for the ISM will be about 1 particle per centimeter cubed. For a GMC, it's going to be a few orders of magnitude larger than that. And the cores of the GMC can go all the way up to about 10 to the 5 particles per centimeter cubed. So there's actually quite a lot of compression. So we take a reasonably sized chunk of the ISM and compress it into the ISM and then into a core that will ultimately make stars. The mass is typically between 10 to the 5 to 10 to the 7 solar masses. And while there is some debate on it, it's widely agreed that the lifetime of a giant molecular cloud is longer than its freefall time. So something is keeping the giant molecular cloud from collapsing on a freefall time just because of gravitation and making all the stars. And also the efficiency for star formation is very small in giant molecular clouds. So a lot of what I'm going to show is based on an idea that was posed by Brent Robertson and Peter Goldreich in 2012. And that's the fact that if we take a chunk of turbulent gas and compress it, it's going to speed up just because of the compression. That speedy V work that's just done because of the compression, causing all the eddies to start spinning up. And that roughly operates like the velocity will scale like 1 over the scale length. The opposing mechanism is dissipation. And dissipation works on a typical time scale. That's an eddy turnaround. So that has been shown by McClure et al. In '98 and by others. And once an eddy turns, a large eddy turns once, it typically loses a big fraction of its kinetic energy. So that's the dissipation rate. And since we have two rates, we can compare them and get the scale out of it. And this scale will determine if the gas is accelerating as it's being compressed or being dissipated and decelerating as it's being compressed. And that's what they showed. So if we start with a compression rate which is smaller than the dissipation rate, the turbulence dies out. That's a function of the scale factor. That's just the velocity. The velocity dies out. If we start with a compression rate which is much higher than the dissipation rate, the turbulence will wind up, will increase. And because there is typical scale, we can pass that scale. So as gas is being compressed, its velocity will typically go up, and the size of the eddy will typically go down. So the dissipation will become more and more dominant, and we can start with an adiabatic phase where everything spins up, and then turn over and start dissipating away. And so how does this relate to giant molecular clouds? So there is one more level of complication to the problem, and that's magnetic fields. We know that there are magnetic fields in the ISM, and some of them, at least, there are some random magnetic fields, and then there are ordered magnetic fields along guidelines, magnetic guide fields. And we know from observations that the molecular clouds know about these fields. So we can see them being aligned with the magnetic fields, being elongated along the magnetic fields. The compression definitely knows about the magnetic fields going on. And this has been shown for many molecular clouds. Basically the same idea. So I'm going to, oh, sorry. I'm going to stop talking about about giant molecular clouds for just a few minutes and talk about turbulence. So how do you drive turbulence? You usually start with just a box of gas in a simulation, and then you need to drive it. And that's a very arbitrary process. You need to choose, first of all, if you're going to drive it by solenoidal modes, which introduce vorticity. They basically churn things up, or by compressional modes. Then you have to decide the wavelength. Because of the cascade, you usually drive the large eddies and allow everything to cascade downwards. And you also have to decide the phase. Do you drive always exactly the same path, or do you change and play with it? And this is a very arbitrary thing. And once the turbulence is driven, if you want to get supersonic turbulence, most of the dissipation will occur by shocks. And that's why if you drive compressional modes, they'll dissipate quite quickly. But if you drive solenoidal modes, they'll survive much longer. And to drive magnetic hydrodynamic turbulence, you usually start with just a trace amount of magnetic fields, and you allow it to increase via dynamo. So the idea behind dynamo is that if we have magnetic loops, and we take some portion of it and start winding it, we'll actually increase it on an exponential scale. And this has been shown. That's the energy in the magnetic field as a function of the eddy turnaround time, and it grows exponentially until at some point it saturates, and the saturation depends on the back reaction between the magnetic forces and the turbulence. So at some point, the power in the magnetic Lorentz forces is strong enough to start affecting the flow, and basically the process stops. And we know this saturation value. It depends again on how you drive it and on the Mach number of the simulation and on some other factors like the dissipation mechanism and the Prandtl numbers and so on. But we know how it's going to react in the driven, for the driven case. Another choice we have to make is if we want to use guide fields or not. So if we don't use, the typical case that I showed you doesn't use guide fields, and basically the winding up is just because of stretching and pulling along magnetic fields within the box. But for the giant molecular clouds, it's probably a better approximation to assume that there is a guide field. And the guide field will act very differently on compression. So while compressing, in principle, this kind of turbulence can die out. The magnetic field can die out. But here, it cannot die out, because once the box is compressed, we basically compress the flux lines, and magnetic field has to go up, at least along the guide field. So just a little bit about the runs that I'm going to show you. They were ran with flash on 512 cubed cell boxes. The gas was isothermal and driven to an initial Mach number of about 10. Instead of contracting the box physically, which is complicated, we used the cosmology model that was already implemented into Flash backwards. So instead of having cosmic expansion, we just introduced compression, negative Hubble constant, and the only thing that needed modification was just the magnetic equation that this was not implemented to. We performed runs with and without magnetic fields, magnetic field guides, and the way we do it is initially we allow the turbulence to settle. We drive it for a few turnaround times. Then we stop the driving and start the compression. Start compressing the box and see how it reacts. So these are the runs that we did, a few hydrodynamic runs, a few runs without a guide field, and a few runs with a guide field, different compression rates, different resolutions. But the main difference between the runs is the amount of magnetic fields that we introduced. So they go all the way from being almost negligible initially to equipartition, and even slightly above equipartition. And that's what we find. So this is one of the plots that I'm going to show you. That's the Mach number as a function of time. The black solid line here is the end of the initial driving phase. So anything here is just the driving phase. We let it settle down. And then at some point, we stop the driving and start the compression. And then we can see the scale factor of the compression here. And if we just look at the blue line, for example, that's the purely HD, purely hydrodynamical line. It acts exactly like the Robertson and Goldreich model predicts. So initially, it winds up, then it passes the dissipation criterion, dissipation becomes important, and then it dies down. So that's exactly what we expect. When we add the magnetic fields, it starts behaving differently. And what we see is that after some time of dissipation, it actually starts shooting up again. And so we compress the box. Initially, it winds up. It starts moving faster. Then it starts moving slower because of dissipation. And at some point, for some reason, that I'm going to explain to you, it actually starts shooting up again. It starts moving much, much faster. And we see that without the guide fields, it's much more pronounced with the guide fields. For the case where we start with equipartition, basically, we never go through a dissipational phase. So what's going on? Another hint of that is in these plots over here. So this is, the x-axis is like before, time and then compression. And the y-axis is the ratio between the kinetic pressure and the thermal pressure in the solid lines, or the magnetic pressure to the thermal pressure in the dashed lines. And we can see that they both go up initially. So the kinetic pressure goes up. And the solid line we see here is just the slope that we expect from the adiabatic compression of kinetic turbulence. And the dashed line here is the adiabatic slope we expect for the magnetic enhancement because of compression. And then dissipation starts, and dissipation is faster for the kinetic component. At some point, even if we start with a subcritical magnetic pressure, the magnetic pressure becomes more important. And this has to do with the fact that dissipation actually goes down, almost disappears. And this is a little different, but roughly the same for the guide field cases. It goes up and then it goes down, and then at some point the magnetic forces become important, and they start, and the dissipation goes down. The lines we see here, the dot dashed lines, is just the pressure that we deduce from the magnetic fields along the guide field. So that has to go up. That was just the flux conservation that I talked about. So here the flow is adiabatic again, and we see that over-magnetized gas doesn't dissipate. So that's a hint. Okay. But again, but now I'm going to show you really what's going on, and there is no replacing actually looking at the pictures. So the top panel here is the initial case after the initial driving for 3 of the runs. That's a pure hydrodynamic one. That's the one with no guide field. And that's the one with a guide field. And initially, they all look roughly the same. The column map at the back of the box is density, and the lines we see is velocity. And the velocity is colored according to its z component. And the guide field in this case, was along the Z component. Initially, it starts the same. And the bottom panel shows the boxes after the compression by 3 orders of magnitude. So that's when the density would have increased by 9 orders of magnitude. That's a much more dense case, but it shows what's going on. So for the hydrodynamic case, we see that the turbulence died out, but the flow is still very random, turbulent. For the two cases where there is magnetic fields, we see a different thing. We see that channels occur, or chimneys, and that the flow is along these chimneys. And it's quite easy to understand why the dissipation is so low for these cases. There is no shear. There is no compression. This is just stuff moving one along the other. It's not turbulence anymore. But this is what happens when you take a turbulent box and you compress it. When we have magnetic field, the turbulence settles into dissipation, less flow. And the reason for that is that most of the dissipation is done via shocks. This is supersonic turbulence and compressive modes. And the scale, the way we drive the turbulence when we compress the gas is scaleless. We are not as arbitrary as we were before in how we drive the turbulence. We basically just take all the modes and pump energy into all the modes at the same time. That's what the compression does. And for this case, we are not mixing the modes. So the modes that would die out because of dissipation just go away. They dissipate away and disappear. And the modes that remain have no dissipation in them. And these can actually grow. And that's the process that we see. So scaleless driving allows decaying modes to disappear, and we are left with the non-decaying modes. I just want to mention that there is a counterintuitive point here, and that is usually when the turbulence is dissipating too quickly, people increase the feedback. People try to wind it up faster. According to this picture, what they actually do is start mixing the modes again. It could actually be counterintuitive, counterproductive. So if we start churning up the gas, the dissipation will actually go up. It will work in the other way than we expect. And that's just another way of showing it. That's the power in compressional modes to the total power in all the modes. We expect it to be between 20 to 60% for driven turbulence, depending on how we drive it. And we see that it goes down as the gas is compressed. All the compressive modes go away, and we are left with very little power in compressive modes. Okay, so are we done? Is this all? In general, we could say it is. I mean, all of this should already be in the simulations. If we have MHD simulations, we can do it. We just need to resolve the cores in Galaxy simulations to resolve the cores with such resolutions in MHD simulations, and we'll be fine. And we can do it on our quantum computers, then get into our jet cars and fly away. Or we have to take a more practical approach, which is to produce subgrid models, and we go on and propose such a model. So we have 3 forms of pressure: thermal pressure, kinetic pressure, and magnetic pressure, and we know how each of them will react separately to compression. So we know that turbulent pressure will behave like an ideal gas with gamma of 5/3. Magnetic pressure, once it's coarse-grained, behaves like a pressure with 4/3, with gamma of 4/3. And we have these 3 buckets of energy, and when we squeeze the gas, we pump the appropriate amount into each of the buckets. And these buckets can also transfer energy from one bucket to another. So shocks, for example, will turn kinetic energy into thermal energy, and this thermal energy will go away. In our case, because the gas is isothermal, actually we just remove energy directly from the kinetic component. And the dynamo effect will turn kinetic energy into magnetic energy. And if the gas is over-magnetized, the opposite process will occur. So we can write terms for this transfer. I don't want to get into the details. It's all in the paper. We mimic what we see here just by transfer term between the kinetic component and the magnetic component. We use the same dissipation, the McLaw 98 dissipation. We have some free parameters that we have to calibrate from the box, but having done that, we can formulate an effective equation of state that connects the total pressure to the total energy. We have to divide the energy into the different components, and we work out this gamma, which is an effective gamma, which will determine how the whole box will react, coarse-grained, to the fact that we are pressing it, compressing it, and we rigorously derive this gamma. We come up with a form that naturally behaves like the dominant factor if there is only one dominant component. It takes into account the fact that we can transfer energy from one component to the other, and seems to behave quite nicely. And this is not, this is almost completely ready to be put as a subgrid model into cosmological simulations. Things still need to be calibrated to that specific code, but there is actually a roadmap on how to do that now. Okay, so that's my conclusion slide. I showed you in the first part that turbulence winds up as we compress it, and that if the gas is magnetized, the dissipation at some point goes to zero, and the compressing turbulence winds up to very high values. Dissipationless flows occur when the system is left alone. And this is counterintuitive. If we try to pump more energy, to drive more energy in the regular ways into the feedback, will destroy the dissipationless flows, and dissipation will be high again. It could be important in increasing the lifetime of giant molecular clouds. We did not show that specifically. All our simulations are box simulations. And it should have an observational signature. This is very different than regular turbulence. We expect gas to be moving in chimneys. We expect it to be aligned along the magnetic fields. All this could be checked by observations. And the second part is that we suggest a model of how to implement all this in subgrid and show that we basically understand the process. Okay, thank you very much.
Questions?
How do you think your box geometry affects the result? For example, with your channel flows, because you have a periodic box, they make the cloud flow back into itself, whereas in reality, it would actually kind of move segments of the cloud apart. And also, in a real galaxy, you'd have some galactic-wide shear, which might modify the outcome.
I agree to both comments. It will make a difference. The periodic box, I mean, if we take a very long filament, it should roughly reproduce the results from a periodic box. But obviously, this is not infinitely true. And yeah, all these geometrical effects need to be taken into account. I agree.
So I like it in general. I have a question about when you look at molecular clouds, which are always filament, you know there are these striations. Perpendicular to the filament, there are these long lines. And
yes.
People argue that this is magnetic field driven. So basically that would contradict to what you say. The magnetic field is perpendicular to the filaments and not parallel to the filaments. So how do you solve this problem?
Well, I think the jury is still out about whether this is actually the case. So the observations of giant molecular clouds I showed in the beginning actually indicate that it does along. So the red lines here, that's Herschel and the ALMA plots. The polarization is from ALMA. And that's the red lines over here. So we can really see that it's, that the,
But the red is actually more perpendicular too. I mean, it's not part of it, you know. It crosses the filament, you know, as you see.
yes.
And the striations are even more extreme. It's really 90 degrees. So that's what one usually sees. So it's actually contradicting.
Well, no, I think,
Well,
okay, yes. And it has to do with the wrapping, with the shearing of the large-scale shearing that will also occur on similar timescales. Yes, I agree that reality is more complicated than the box.
How does this magnetized version of turbulence affect the density distribution?
Okay, so we did not directly compare the PDF that we get from the magnetized simulation to the non-magnetized, but the reason we did not do that is that we don't expect it to make a really big difference for this case. This is not, what we did not resolve here at all is the initial multi-phase gas. So we start with just single-phase turbulence here. And ultimately, what has to be done is to start with a warm component and a cold component, and then we can really make predictions for the PDF.
More questions? If not, let's thank you again.